Okay, this chart is giving the depth of a snowfield is given by a twice differentiable function s, where s of t is measured in centimeters and time is measured in hours. The values of the derivative s prime of t are given in the chart. And it's also known that the graph of s is concave down. Remember, concave down means it's like a frown, so it's upside down parabola type shape. So this problem says use the data in the table to approximate s double prime of 10, the second derivative, and show the computations that lead to the answer. So s double prime is the derivative of the derivative. So it's the slope of the tangent line to the s prime. So since we're provided s prime, we're really just looking for the derivative of s prime. Now, of course, we're only given a chart full of some of the values, and in particular, we aren't given 10. But since the slope of the tangent line is the limit of the slope of the secant lines, I'm going to use the points 8 and 12 to estimate the slope of the secant line. Or sorry, to get the slope of the secant line, which estimates the slope of the tangent line. So I'll do the A rock between 12 and 8. So I'll do f of b minus f of a over b minus a, which provides negative 0.2 divided by 4, which is negative 0.05. And our units would be the s prime, which is the centimeters per hour, per t, so per hour, or more appropriately, maybe negative 0.05 centimeters per hour squared. Okay. As far as describing what this means in the context of the problem, it means that the rate of change of the rate of the snow is going down by 0.05 centimeters per hour squared. Right? So it's almost like an acceleration for lack. Okay. In part B, it says, is there a time between 0 and 14 when the depth of the snow is changing at a rate of 2 centimeters per hour? Well, that's actually true by the intermediate value theorem, if you think about it, because at time equals 3, the rate of change of the snow is at 2.1, and then at 8, the rate of the change of the snow is 1.9. So since this is a twice differentiable function, which means it's continuous, that means that between 3 and 8, somewhere between 3 and 8, you must have hit 2. So by intermediate value theorem, there is a time between, in fact, we know where it's between 3 and 8, t equals 3 and t equals 8, when s prime of t must be equal to exactly 2, because that's the intermediate value theorem on this continuous function. Okay, the last problem is at time equals 8, the depth of the snow is 45. So S of 8 is 45. S of 8 is 45. Furthermore, from the chart up here, we know that S prime of 8 seems to be 1.9. So given a point and a slope, we are able to make a tangent line to the curve of S, right? Wherever it is, we're going to make this tangent line to S. So the tangent line would be y minus the y coordinate equals the slope times x minus the x coordinate. So there is the equation of the tangent line, like it's asking the tangent line, and they want us to use this to estimate the actual depth at the time equals 10. So I'm going to take this and I'm going to replace x for 10. So it looks like in that case, the y would be equal to 1.9 times 10 minus 8 is 2, and then add 45. And of course, 1.9 times 2 is 3.8, added to 45 is 48.8. And I guess the context here is centimeters of snow. So it was 45, and now this model is predicting it's going to go up to 48.8. It also asks whether it is an overestimate or an underestimate, and that comes from the concave down nature. So if you notice that whenever I draw in tangent lines on this frowny face, all of the tangent lines are overestimates. So it turns out when something is concave down, your tangent lines will overestimate the truth. And so that's the answer to that part of the problem.